about the BCD codes, and we have done some examples of the BCD addition. BCD is nothing but it is a binary coded decimal. It represents 10 decimal numbers ranging from 0 to 9, and it requires 4 bits. As with the 4 bits, we have total 2 raised power 4, that is 16 combinations, and here in case of BCD, we are using only 0 to 9, that is 10 combinations. So 6 states are unused, which are not used in the BCD. As in the previous example, we have done the addition of 2 numbers. One is 763 and another one is 549, and we have to add it using a BCD addition. Now, what we do first, first of all, we have to convert all the given number, or we have to represent all the given number with the equivalent BCD code. As in this case, 7 is represented by 0111, 6 by 0110, 3 by 0011. Similarly, we represent 549 as in BCD, and we just add like a normal binary sum. Now, if in the sum there is any unused state, that means the term in the sum is greater than 9, then we have to add 6 to all the terms, and the final result after addition will be your BCD answer. So here in this case, all 3 terms are greater than 9, then we have added 6 binary 6 to all the 3 terms, and we get our answer here, and this answer can be verified by simply a decimal addition. Now the answer should be 1312. Here the answer is same, is 1. It may be represented as 0001. 3 is 001, 0011. 1 is 0001, and 2 is 002. So this is a type of code BCD which is used to represent the decimal number. There are some more decimal representation, the different types of code in which we can represent decimal numbers. So we can look into the table that there are more further 4 different binary codes for the decimal digits, which are widely used to represent decimal number. So here are your decimal digits 0 to 9, and here are your first code that we have studied so far, that is binary coded decimal, BCD, and it is also known as 8421 code because each digit has its equivalent weight. That means the MSB has a weight of 8, next bit is weight of 4, next bit is weight of 2, and the LSB, that is the least bit, has a weight of 1. So I can say that this bit is 2 raised power 0, 2 raised power 1, 2 raised power 2, and 2 raised power 3 is equals to 8. In this manner, we have written here the codes. 0 is represented by 0, 0, 0, 0, 0. 1 is represented by 0, 0, 0, 1, means 1, LSB is 1, then its weight is 1. So if I see 6, here 6 is 0, 0, 0, 1, 1, 0. That means I am adding the second bit is 1, that is 2. Next bit is 1, 4. 2 plus 4 is 6. So its decimal equivalent is 6. Similarly, for the 9, I have 8 is MSB is 1, that is 8, and LSB is 1, that is 1. So 8 plus 1 is 9. Now, in this way, we can write the BCD code, or we can say these are the weighted code denoted as 8421 or BCD simply. Another code is with the weight of 2421. So 2421, again, this is the weight of the particular coefficient. If I say I have to write 5, okay, let's start from the beginning. 0 is 0, 0, 0, 0. For 1, what I do, I have made LSB equals to 1, then the code is 0, 0, 0, 1. For 3, it is 2 plus 1. So, for 3, it is 2 plus 1. So, 2 is here and 1 is here. So, code is 0, 0, 1, 1. For 2, I may write like 0010. So this second digit has a code of weight of 2. For the 5, I have 2 plus 2 plus 1. So it is 1 0 1 1. For 6, it is 4 plus 2. So 4 2 1 1 0 0. It is 4 plus 2 plus 1. So 1 1 0 1. For 8, it should be 2 plus 4 plus 4. So 1 1 1 0. And for 9, it is 4 plus 2 plus 2 plus 1. So it is 1 1 1 1. So this is the way how the weight is added in the to the coefficients. So whichever bit is 1, that is added, that total sum is added, and the correspondent decimal number is represented by the 2421 BCD code. Another very useful code which is used is the XS3 code, and the name comes from the as XS3. It is nothing but BCD plus 3. Means we have to represent the number by BCD, and we have to add it to the we have to add it 3 into the BCD number. So in the case of 0, 0 is represented as 0 0 0. So I add 3 into it. So 0 plus 3 is 3. So the code for 0 in XS3 is 0011, which is equivalent to 3. In case of 1, if I write in BCD, it is 0001. So if I add 1 with 3, it will be 4. So then the code of the 4 is 0100, that is equals to 1 in XS3. So XS3 is nothing but it is BCD plus 3. We write BCD code and add 3, just represent by its binary equivalent. So another code is 84 minus 2 minus 1. It is again weighted code. So we add weight of the so if I have to write 0, then it is 0000. If I had to write 1, then it should be 4 minus 2 minus 1 equals to 1. So I have made 0 1 1 1. If I have to write 2, then 2 should be 4 minus 2, 0 1 1 0. If it is 3, then I have to write 4 minus 2 sorry 4 minus 1. So 0 1 0 1. If I have to write 4, then it should be 4. So 4 is 0 1 0 0. If I have to write 5, then 5 should be 8 minus 2 minus 3. So it is 1 0 1 1. For 6, it should be 8 minus 2. So 1 0 1 0. For 7, it should be 8 minus 1, 1 0 0 1. For 8, it should be 8, so 1 0 0 0. And for 9, it is 8 8 plus 4 12 minus 2 minus 1, that is 9 1 1 1 1. So these are the methods, or these are the techniques how the codes are written, and in each case we can say we are using only 10 digits to represent decimal number. So rest 6 digits or next 6 combinations are unused, which are not used to represent the decimal number. So whichever code is missing in the 16 combination, that is written in the downward, which is I have written simply unused bits. So these combination or these distinct combinations are not used for the particular type of code. Uh, Further, we moved, then we can characterize the decimal codes in two terms. The first is weighted code. The each in weighted code, each bit position is assigned a weighting factor to calculate the value of the number. And the example of the weighted code are 8421 normal, your first BCD, 2421 code, and 84 minus 2 minus 1. We can simply see here that in all three cases, BCD 2421 and 84 minus 1, the weight whichever position is 1 in this particular code, that particular weight is added and the corresponding decimal digit is obtained. So we say that 8421, that is BCD, 2421 and 84 minus 2 minus 1 are known as the weighted codes. Another type of characterization is a self-complementing code. That question was asked last year in the first term examination, midterm, that what are the self-complementing codes. So how we define the self-complementing codes? The nines complement of a decimal number is obtained directly by changing 1 to 0 or 0 to 1, which is in the case of ones complement. And here the 2421 and XS3 codes are known as self-complementing code. So we can look into the table. For the 0 is 0011, and its nines complement of the 0 should be 9. If I change 0 by 1 and 1 by 0, it should be 1100, which is correct. Again, we can see that the nines complement of 1 should be 8. If I complement this number, it should be 1011, 1011. So 2421 and XS3 both are the self complementing codes. So two type of decimal codes are there. One is a weighted code, in which we add the weight of the corresponding bit, which is whose value is 1. And next, another type of code is self complementing code, in which we change 0 by 1 and 1 by 0 and obtain the nines complement of the particular decimal number. So let us example how to write XS3 codes. All of you solve it in your notebook. We have to represent 356 in BCD as well as in XS3 code. So what you do first, first convert the 356 in BCD. All of you write the BCD code for 356. 3 is represented by 0011, 5 is represented as 0101, 6 is represented as 0110. So the BCD code should be 0011, 0101, 0110. Is that correct?
Yes, sir.
Okay.
Yes,
Now
yes, sir.
in each bit you have to add 3. Now for 3 you have to write the code. 3 plus 3 is 6, you have to write the code for 6. For in case of 5, you have 5 plus 3 is 8, you have to write the code of 8. And 6 plus 3 is 9, you have to write the code for 9. So convert these codes. So I think this should be like this: 3 plus 3, 6. So 6 is 0110. 5 plus 3 is 8, it is 1000. 6 plus 3 is 9, it is 1001. So this is your XS3 code for 356. We're getting it?
Yes, sir.
Okay, now let's move to the next type of code. Code is gray code, which is very important in continuous data transmission, and it is also known as error detecting codes, which detects error when we are transmitting a continuous data over a line. Now how these codes are represented and how these are important: the output of many system usually produces continuous data. If you are transmitting a continuous data like a sequence 0 1 2 3 4 5 6 like this, so the advantages of gray code is that only one bit in group code changes when going from one number to the next number. Suppose if I take an example of the different codes here in this table. Now when I am moving from 0 to 1, so 0 to 1 in case of BCD only one bit is changed, that is the LSB. Now when I move from 1 to 2, bits are changed. This in the LSB is changed from 1 to 0, and the next bit is 0 to 1. Now again if I consider the case, then when I am moving from 7 to 8, so when I am moving from 7 to 8, all 4 bits are changed, LSB is from 1 to 0, next bit 1 to 0, next bit 1 to 0, next bit 0 to 1. So gray codes are such type of code in which only single bit can change when we move from one digit to the next digit. Suppose I am going from 0 to 1, then there will be only one bit change. If I move from 1 to 2, there should be a one bit change. If I move from 2 to 3, there should be one bit change. So when we are transmitting a continuous data over a line, then it checks that number of bits changed in from one bit to the another bit, it should be one. So when I'm transmitting from a transmitter and there is a receiver, and I say that the data is over gray code, then every time it receives a data, it will check the number change in the number of bits. If the number of bit change is one, then the data is correct, it is okay, it acknowledges the data is correct, I have received. In the case when I am transmitting two digits and the receiver detects that the number of bit change is more than one, then it sends an acknowledgement to the transmitter and says that I have received a defective data, and in this manner, so we detects that the data received is a faulty data. It will send a request to the transmitter, it will resend the data. So this is the way how the error is detected while we are transmitting a data from a transmitter to the receiver. So here we try to write the BCD codes, sorry, accessory codes. So advantage gray code is that only one bit in the code group changes from going from one level to the next level. So here we can find out. So you can see these are the decimal number 0 in the binary code. It is represented by 0000. In case of gray code, it is 0000. When we move from 0 to 1, it is 0001. In case of gray, it is also 0001. So change in number of bits is 1. Now here when we move from 1 to 2, in binary 2 is represented as 0010. So there is a 2-bit change. Now in case of gray code, we write 2 as 0011. So number of bit change is only 1. Change from 1 bit change from 0 to 1. Now to represent 3, we write 00 in case of 3 in binary, again there is a single bit change, but in case of gray code I write it like 0010. Again the number of bit change is 1. When we move from 3 to 4, there is a 3-bit change in binary code because it is 0011 and it becomes 0100. Now in case of gray code, it is 0110. So again the number of bit change is 1. Third bit is changed from 0 to 1. In case of 5, I write like 1111. So there is again a single bit change here. The bit change is single bit, that doesn't matter. In case of 6, here we write it 0101. In case of 7, it is 0100. 8 is 1100. So you can see in consecutive numbers, the number of bit change is only 1. 9 is represented at 1101. 10 is represented as 1111. Again the number of bit change is only 1. 11 is 1110. 12 is 1010. 13 is 1011. You can see the number of change in two consecutive bits is only 1. 14 is 1001 and 15 is 1000. So you,
सर
yes,
सर
बोलो।
मैं कह रहा हूँ सर आपने ग्रे कोड कैसे लिखा है सर, एक बार फिर से बता दो ग्रे कोड कैसे लिखा आपने
हाँ, तो
सबका, ये भूल गया मैं शायद।
अभी हम नेक्स्ट टॉपिक पे आते हैं, ग्रे कोड को कन्वर्ट कैसे करते हैं। तो ये तो हो गया रिप्रेजेंटेशन, जस्ट आई हैव शोन यू हाउ टू रिप्रेजेंट ग्रे कोड्स। तो दिस टेबल इज जस्ट फॉर लुकिंग दैट इन ईच डिजिट और ईच कंसेक्यूटिव
अच्छा
नंबर देयर इज ओनली सिंगल बिट चेंज। नाउ विल
ठीक।
learn the technique how to convert a binary number into gray code and convert gray code into the binary, because when the data is manipulated in your computer, the computer will not deal with the binary code. It will convert this, computer will deal only with the binary code. What will it do when it receives the data in the gray code? It converts it from gray code to the binary code. That's the process. So we'll learn the technique how the number are converted between binary to gray and gray to binary. Because at the transmitter end, when you are transmitting a data, you have only binary number. So you have to convert these binary number into gray code, and at the receiver end you will convert this gray code into the binary code. So we have the algorithm how the information is interchanged or representation is changed, binary to gray and gray to binary. Here this table is only for looking that in two consecutive numbers we have a single bit change. Fine.
Okay, sir.
So let's move. Now we have when we have to convert a gray code into binary code. So this is the number conversion. Uh, Let us just see the algorithm. Then I'll explain that how to convert it directly. So suppose we are given a gray code and which is represented as G3, G2, G1, G0. So we are taking only 4-bit gray code, and we have to represent it into the binary. Then the process will be like this. We write the gray code. Gray code is given like G3, G2, G1 and G0. The MSB of the binary code will be same. So whatever is the MSB of gray code, that will be the MSB of the binary code. Fine, that is the first step. Do you know about the XOR gate? Have you studied about XOR gate in the first year?
Yes, sir.
Okay, fine. So what we do, this plus sign with the circle is XORing. So next bit, next what we do, we XOR G2 by B3. So these both are XOR. So XOR करने के बाद we'll get whatever is the result, that is your B2. Fine. Just XOR G2 by B3 and get B2. Then again we XOR G1 by B2 will get B1. So B1 is G2 XOR G1. Then again we XOR G0 by B1 and we'll get B0. This is the process, and this process ends until whatever is the length of your string, n number of gray code. You have to convert this into the n number of the binary code. So I again explain the algorithm. First, the very first point is the MSB of the binary code and the gray code is same. In the next step, we XOR MSB of the binary code to the next bit of the gray code and find B2. Next, we'll XOR B2 with next bit of the gray code, that is J1. So B2 XOR G1 is, then we XOR B1 with the G2, we'll get B0. And this process continued until n number of digits. So here we can summarize that B3 equals to G0, B3 equals to G3, B2 equals to G3 XOR G2, B1 is B2 XOR G1 and B0 is B1 XOR G0. We'll take an example, then it will be much more clear. Now suppose you try to solve this question in your copy. We have a code 1001 and we have to convert it into binary. You can look into the table of the XOR gate. If both input are 00, then the output is 0. If the input is 01, output is, if the input is 10, output is 1. If the input is 11, output is 0. Or I can summarize it at like if both inputs are same, 00 or 11, then the output is 0. If both inputs are different, then the output will be 1. So we follow the same process. MSB is same, 1. Then 1 XOR 0 is 1. 1 XOR 0 is 1. 1 XOR 1 is 0. So this is your binary code 1110. So gray code is 1001 and binary code is 1110. You note down and we'll check in the table. Here we can say what was the binary code 1001. Binary code is 1001 and the gray code was 1001 and the binary code is 110. So this is the way you can convert a gray code into the binary code. So it is gray code is 1101 and the binary code is 1110. Is that correct? Now do this example with yourself. Now convert the gray code 100011 into binary code. This is your gray code. Write down in the copy. Now what should be the MSB? First binary code will be anyone in the class. First binary code MSB.
वो नहीं होगा ना सर.
1 sir 1.
1. तो ये हो गया. First MSB is 1. Then we'll XOR 1 0 equals to 1. Then again we will XOR 1 0 is 1. Then 1 0 is again 1. Then 1 1 is 0. Then 0 1 is 1. So this is the way how we convert gray code into the binary code. So again we can look it into MSB is same.
सर इसमें कैरी नहीं होगा क्या?
कोई कैरी नहीं है. XOR में कैरी नहीं है. In we are not adding, we are just XORing. XOR का means है अगर both input are same 0 0 or 1 1 then the output is 0. If both are different then the output is 1. That's it. No carry. We are not adding, we are just logically XORing. Okay. So first MSB is same. When I XOR 1 and 0, 1 0 input are, one input is 1, another input is 0, then the output is 1. Next I XOR 1 with 0, output is 1. 1 with 0, output is 1. 1 and 1, output is 0. 0 and 1, output is 1. So you need not to worry how to convert, how to remember the gray code for a particular binary number. Whenever it is asked, you can directly change a gray code into the binary, and in the next step we'll move how to convert binary code into the gray code. Is that clear now, how to convert gray to binary number?
Yes sir.
Yes sir.
Okay, fine. Now move to the next step when we have to convert binary number into the gray code. So you are given a binary number, you have to convert into the gray code, and that process is done at the transmitter. The previous process when we are converting gray code to the binary code, that is done at the receiver end. So suppose now that you know to convert gray to binary, we shall learn the reserve technique. Let the binary code be B3, B2, B1 and B0. These are the binary digits, and we have to convert it into the gray code. The process is like this. MSB is same. Whatever is B3 will be G3. We XOR B3 with B2 and get G2. We XOR B2 by B1, get G1. We XOR B1 by B0, get G0. XOR operation is same if both digits are same, then the output is 0. If both digits are different, then the output will be 1. That's it. So here we can summarize it. B3 equals to G3, G2 equals to B3 XOR B2, G1 is B1 XOR B2 XOR B1, and G0 is B1 XOR B0. So in the previous case we are cross XORing, here it is consecutive XORing of the bits like this. The process is only XOR. We take an example of this. Suppose we are given a number, binary number 1110, the last one which we have converted. The binary number given is 1110, and we have to obtain the gray code. So the first step is MSB same, then 1 XOR 1 is 0, 1 XOR 1 is 0, 1 XOR 0 is 1. So simply you can see what we have done in the last conversion, gray to binary, and this is binary to gray. The process is XOR, but the bits are only changed. Is that correct? Are you getting it or not?
हाँ सर,
ठीक
yes
है,
sir.
Yes, sir.
तो ये एग्जांपल अभी मैं बता रहा हूँ, ये वाला एग्जांपल आप सभी लोग कॉपी में करेंगे. We have to convert the binary number 11101 in gray code.
Sir,
First,
1000111.
11101. So we do step by step. For the gray code, MSB will be same. So we write the MSB. Is that correct? Next, we XOR 1 by 1. Then the output is 0. 1 by 1, output is 0. Then again, we XOR 1 by 1. Output is again 0. For the next bit, 1 XOR 1. Output is 0. 1 XOR 0. Output is 1. 0 XOR 1. Output is 1. So this is the way how we convert a binary number into gray code. Is that clear?
Yes sir.
Write down this question. This is for the home learning. You can convert it and verify your number. Convert binary number 10110101 in gray code. Then again convert binary gray code to the binary number and verify your answer. So initially when you convert binary number into gray code and when you again convert into the binary number, both numbers should be matched. This is your some sort of assignment, or you can say the practice example. Further, some question will be there. What I have shared you the assignment sheet.